Hello friends, today we will discuss a problem from I.S.I 2017, B.Stat and B.Math entrance. And this particular problem has a very simple statement. It's almost deceiving how simple the statement is. It says that SB the square, so this is the square that we have drawn, uh, formed by the four vertices, that's 1, 1, negative 1 1, negative 1 negative 1, and 1 comma negative 1. So it's a standard square, and R be the region or the set of points inside this square. Inside this square there are certain points which are closer to the center. So let's draw the center. The center is, suppose it's here. So this particular region R that we are interested in, it is a set of points which are closer to the center. So they are closer to the point O than to any of the four sides. So for example, if you take a point which is really close to this point O, suppose let's call this point P, that point will be one of the points inside the region R. Of course, there are plenty of other points, and in fact, we would want to exactly describe the region R, and not only that, we would want to find the area of the region R. For example, let's take the distance of the point O from one of the sides. Let's say AD, this particular side. So, any point which is before the halfway mark, any point which is before the halfway mark will be in the region R. Any point which is after the halfway mark will definitely not be in the region. Of course, we have to be careful about this now, because we want these points which are in the region R not only closer to O compared to the side AD, we want them to be closer to O compared to the side AB, BC, and CD as well. So that is the starting point of this problem. Now let's look into this phrase, which are closer. What does the problem mean by that? So let's isolate the picture a little bit and work with just AD and a point O, which is the center. So we want all the points which are closer to O than to AD. Now, of course, we have to think about other three sides as well eventually. But for the time being, let's think about it like this, that let's figure out those points which are closer to O than to AD. Now, there should be some sort of a borderline between them, right? Borderline points. What do I mean by that? Points which are equidistant from O to AD. So let's mark the two distances in blue. So if we can mark the borderline points, if we can find out the borderline points, then the points on one side of the borderline will be closer to O than the points which are on the other side of the borderline, right? So goal is to find the borderline points. And what do I mean by the borderline points? The points which are equidistant from O and AD. Now this is a very standard locus definition of a parabola. If you recall from your coordinate geometry lessons, that what is a parabola? A parabola is the locus of all points which are equidistant from a fixed point O, which we often call the focus, and a fixed line L, and a fixed line L, which is often called the directrix, right? So in this case, we are interested in that parabola which has AD as the directrix and O as the focus. So it will clearly look somewhat like this, right? So these points on the parabola, of course this is not drawn to scale, so these points on the parabola are equidistant from AD and O. Now we have found the borderline points. Any point which is on this side of the borderline or the bordering parabola, they would be closer to AD, and any point which is on this side of the parabola, they would be closer to O compared to AD. So we would be interested in all points which are in this zone. Of course, then we have to also worry about other sides, all the other three sides. So given that you understand this, let's look at a short animation of what we are talking about. Now let's repeat the experiment that we are talking about with the side CD and the point O. So what we will do is we will trace out the points which are equidistant from CD and O, such that points on one side of that borderline would be closer to O and points on the other side would be closer to CD. And keep in mind that eventually we will be interested in working with all the four sides together. But for now, let's talk about only the side CD and the point O. Clearly, we have to start with marking the midpoint or the point which is in between O and CD. So let's mark that, let's call that M. Next, let's join OM, which is of course half unit long, and then drop a perpendicular from M to CD, which is also half unit long. And then let's start moving M in a way such that it's equidistant from O and CD. So let's start moving M in a way such that it is equidistant from O and CD. Notice that it's tracing out a parabolic shape, and it's of course hitting the midpoint of the two sides of the square, two other sides of the square, because if you see, it's very clear that if you take the midpoint of, let's say, AD, or if you take the midpoint of BC, then those points are of course equidistant from O and C. So if we stop the animation and if we move to the midpoint of BC, clearly that point is equidistant from C and O, and hence it's part of that parabola. So now let's trace the point M, and you will see clearly that it's defining a parabola. It's basically one of the four parabolas that we will be interested in eventually. One between O and CD, which is this. So similarly, we will have a parabola that is between O and AD, O and AB, and O and BC. So these are the four parabolas that we are interested in. And the region that is between or enclosed by all these four parabolas, that region is the region R. Let's mark the 4 points of intersection of the four parabolas, and this region EFGH, you can easily see it's the common region which is closer to O compared to any other sides, and this is the region whose area we are interested to compute. This is my region R. Now that we understand what the region R is, I mean, computing the area of the region R is really very simple. In fact, if we compute the area in the first quadrant, that is this much approximately, then we can just multiply that by 4 and we would be done. So first we have to find out the point F. Now there are different ways of course finding out the point F. One way could be we could use the equations of this parabola and this parabola, and then we can try to solve those two things. There is one simple way that comes to mind, which is this particular point F, by definition, it's equidistant from all these three sides, right? So if the length of this one is t, OF is t, then the length of this portion is also t, and then the length of this portion is also t. So if you drop a perpendicular from F, if you drop a perpendicular from F to the line to the x-axis, then the length of this much is 1 minus t, because the full length of this side is 1, and similarly the length of the height is also 1 minus t. So we have a right angle triangle here, and then we can do the computation. We can use the Pythagorean theorem by setting t square is equals to 1 minus t square plus 1 minus t square. So this would be t square equals to 2 times 1 minus t square. Since t is greater than 0 and less than 1, therefore we can take the square root. Everything is positive, so we can take the square root on both sides. So t is equals to square root of 2 times 1 minus t, which tells us that t equals to root 2 minus square root of t, square root of 2t. In fact, this would mean that t times 1 plus root 2 is square root of 2. T is equals to square root of 2 divided by root 2 plus 1. And in fact, we can rationalize this. We can multiply by root 2 minus 1. Root 2 minus 1. Which would give us root 2 times root 2 minus 1, or 2 minus square root of 2. So this is t. We are however interested in 1 minus t, because that would give us the coordinate of the point F. So 1 minus t is 1 minus 2 minus square root of t, which is square root of 2 minus 1. Coordinate of the point F is square root of 2 minus 1 comma square root of 2 minus 1. So we know now that if we integrate this upper parabola, or this one, from, so let's call this parabola 1. So if we integrate parabola 1 from 0 to square root of 2 minus 1 and add to that the area of this much. So let me zoom in a little bit. Add to that the area of this. Then we would get what we desire, and we can multiply that value by 4 to get the area of the entire region R. So how do we compute the area of the green region? Well, it's also very simple. If we call this parabola 2, let's call it parabola 2, then we have to integrate parabola 2 from square root of 2 minus 1 to half. And how do I know the parabola is passing through the point half? Well, it's because point half is halfway between point, the center and the line AD. So clearly point F is part of the parabola. If we can find out these two values, the two, if we find out the value of these two integrals, we are done. Now what is the equation for parabola 1? Let's do a short recap of how it's done. Let's pick an arbitrary point T on this parabola and let's join the center with from O to T and then drop a perpendicular from T to the line AB, the side AB. By definition, the length of OT is equals to the length of TR. That's how the parabola is defined in the first place. It's a borderline parabola between AB and O, and distances of points from that parabola is by definition equal from the side AB and to the point O. So what is the length of OT? Suppose if the coordinate of T is h comma k, then OT is square root of h square plus k square, and TR is simply 1 minus k, because this length is k, the height. This is 1 minus k. TR is 1 minus k. So if we square both sides, we get h square plus k square equals to 1 plus k square minus 2k. So we get h square equals to 1 minus 2k. This k square cancels. So the equation is x square equals to 1 minus 2y. Of course, we want to integrate it eventually, so we can write it as y equals to 1 minus x square by 2. So we would want to integrate this particular function from 0 to square root of 2 minus 1. So integrating from 0 to square root of 2 minus 1, we would get some value which would correspond to the area in the black shading. Now we want to find the area in the green shading. So to do that, again we find the equation of the parabola, the second parabola. We pick a point S on this second parabola, join it with O, and this side is AD. Suppose if it's h comma k, then again we have square root of h square plus k square equals to 1 minus h in this case, because this much is h. If we square both sides, we get h square plus k square equals to 1 plus h square minus 2h. H square cancels, so we have k square equals to 1 minus 2h, or k equals to positive square root of 1 over 2h. It's positive because obviously we're in the first quadrant, so both x and y are positive. So the equation would be y equals to square root of 1 minus 2x. And we would want to integrate that from square root of 2 minus 1 to half. So if we add these two integrals and then multiply this entire thing by 4, we would get the desired result. Let's have a final look at the picture one more time. So we have found two integrals. One of them is this one, whose value we computed to be square root 0 to square root of 2 minus 1, 1 minus x squared by 2 dx. And the other integral is this, the green portion, whose value is square root of 2 minus 1 to half 1 minus 2x dx. And finally, if we compute these two integrals using standard techniques of definite integration, the value would come out to be this fairly complicated looking number.